I'm going to be talking about joint work with Roland, who's here. So there's probably a bunch of sign errors and other typos, all of which are due to me and nothing to do with Roland. I didn't get a chance to send in the slides in a timely fashion. So what I'm going to be talking about is something we've heard many talks about before at these workshops, which is self-dual Yang-Mills theory. So just as a reminder, self-dual Yang-Mills theory is very simple. It is fields A, which is an ordinary gauge field, and a Lagrange multiplier field B, and with this very simple action. So B enforces the condition that the fields run to self-dual. The reason people are interested in this is that self-dual gauge theory is a funny limit of ordinary Yang-Mills theory. If we add on this term, it's like g squared trace p squared. As you can see, I already got that factor wrong. And we integrate out b, then we get the ordinary Yang-Mills action up to a theta angle, which will be play a very important role here. So one thing we've liked, the subgroup of us who are really like twistor methods is to try to say things about Yang-Mills theory by starting with the self-dual theory, which is very nice, in a sense solvable, and perturb it and see how much you can say about actual gauge theory. So most of the work on this topic up to now has been in perturbation theory. So in this talk, I want to discuss a bit about what we can say about non-perturbative aspects. So one reason people like self-dual Yang-Mills and self-dual Dior is that the infinite symmetries, like the W1 plus infinity symmetry of gravity and the S algebra symmetry of Yang-Mills theory, they're really transparent in the self-dual theory. And I was doing some work with Natalie, and Anthony did some work, he's in the audience here, where you can use chiral algebras built from self-dual gauge theory to bootstrap perturbative amplitudes of QCD in very special situations. There's also some work people have done about top-down constructions where there are dualities between four-dimensional theories and two-dimensional CFTs. But again, these are all are best understood in the self-dual sector. But everything that's been discussed here has been in perturbation theory. Now, in perturbation theory, self-dual gauge theory is scale invariant. It doesn't have a beta function. But non-perturbatively, it does have a beta function. The non-perturbative completion includes instantons. And, well, there's a nice paper of Losev who computes the beta function. And what he sees is that the theta angle flows. So the first part of my talk will I'll explain how the orgy flow of this theory relates to the familiar orgy flow of QCD, and we'll give a new computation of the orgy flow, which is very simple and just uses the index theorem. And then I'll talk about instanton contributions to scattering amplitudes. And this will allow us to understand how this enhanced symmetry behaves when we have instantons. And finally, I want to say a little bit about UV and I-order divergences that arise when one has instantons. Okay. So to understand why this theory must have an orgy flow, let's look a bit more carefully at the theta angles. When I integrate out b squared, well, let's introduce a theta angle. I'll call it theta self-dual for this self-dual theory. And when I integrate out b squared, we don't just find the f wedge star f Lagrangian, we find f minus wedge f minus. And those differ by a theta angle. So integrating out b gives us this Lagrangian here, which is ordinary Yang-Mills theory, plus a theta angle, which is 1 over d squared plus the self-dual theta angle. Okay, so this tells us the self-dual theta angle and the QCD theta angle are not the same. We have this equation. The self-dual theta angle is the QCD theta angle plus 8 pi squared I over g angle squared. So essentially, the self-dual theta angle is the holomorphic coupling. Now, why does this tell us the self-dual theta angle has to flow? Well, we know the QCD theta angle can't flow, at least to leading order by priority conservation, whereas the coupling constant does flow. So therefore, this must flow. And the flow of the coupling constant, it involves a g cubed. So that's precisely what you need to see that the flow of the self-dual theta angle is just, it doesn't have any powers of theta over here. It just flows by a constant. The factors of pi and everything all cancel out, and it just flows by this famous number, 11 over 3 nc, 2 3 nf, and a 6 ns. So the theta angle just flows by adding on I times that number. So what does that mean? Well, if I say q is the exponential of the theta angle, then instantons, instanton number k, are weighted by q to the k. And we're saying that this quantity depends on the scale. So it depends on the scale. It's like the scale to the power of b0. So basically, q has dimension b0. And if I'm in an asymptotically free theory, what happens is that in the UV, instantons are suppressed. Now, we've given a derivation of this from the standard beta function. As I mentioned, there's a paper of Losev where he just computes the one-loop determinant. And I think there's old papers from the 90s which also compute the one-loop determinant in instant moduli space. But what I'd like to do next is give a new computation of this using index theory. Okay, and this is going to give a new way to compute the orgy flow of QCD without actually doing any work with Feynman diagrams. So you might wonder why you would want to do this. But if you've ever tried to suffer through this calculation, I mean, getting the factors of 11 over 3 nc and everything, it's kind of a big pain. Whereas this computation is extremely trivial, and you get the right numbers in like 2 lines. So I think it's the best way to do this. So this computation, well, I think I skipped a slide. Yes. OK. So this computation uses twistor space. So twistor space, I know people have been through many talks about this in this collaboration, so I'm not going to spend much time in it. So twistor space is O1 squared over CP1. And it's essentially, this is well known. It's essentially due to Ward, but I think the Lagrangian formulation is due to Lionel. That self-dual gauge theory lifts to a theory on twistor space with this Lagrangian, where I have a field A, which is a 0-1 form. So A can be viewed as a variation of the holomorphic bundle on twistor space. And B is a Lagrange multiplier field. So we're going to compute the orgy flow of this theory on twistor space. Now, the equations of motion tell us that A is a holomorphic bundle. And a very old result of Ward, this is the origin of the ADHM construction, tells us the moduli of instantons is the moduli of holomorphic bundles in twistor space. With some technical conditions, on each CP1 they must be trivial, and also the holomorphic bundle must be trivial asymptotically at infinity. So what's flowing in our theory is there's a one-loop measure, a determinant, on this moduli space. And the orgy flow tells us that measure scales. Okay. So I'm going to compute that by using the index theorem, as I said. So what are really the index theorem? I'm just going to be the Grothendieck-Riemann-Roch formula. It always annoys me a little bit. Well, anyways, let me see this in a sec. So twistor space has a scaling, where I scale these fibers. And that scaling is just the dilation action over 4. And the orgy flow is an anomaly for that scaling. And we know how to compute anomalies. So we're going to compute it using the Grothendieck-Riemann-Roch formula, 1957. Annoyingly, most physicists don't cite Grothendieck. It's one of my pet peeves. They cite papers from 25 years later. But this is extremely beautiful. There we go. So the Grothendieck-Riemann-Roch formula, actually, there's his commentaries about this. He somehow seemed to think this result was evil when he wrote about it in the 70s. I think he felt, time could have been better spent on addressing societal problems. But anyway, the formula tells us that the first Chern class of the determinant bundle is the integral over twistor space of the Todd class times the Chern character of a certain bundle. Now, the bundle is a very simple thing. It just has contributions from the field content of your theory. Now, we're not interested in, this determinant line bundle, its first Chern class will be an anomaly to the existence of the theory. That's a gauge anomaly. We're not interested in gauge anomalies. We're interested in anomalies for the scaling. So if I want to use anomalies for the C star action, what do? We replace characteristic classes like the Todd class and the Chern character. We simply replace them by their equivariant versions. So we look at the C star equivariant Todd class and the C star equivariant Chern character of this vector bundle. What this anomaly measures is it measures the equivariant first Chern class of the determinant line bundle. So if this quantity is not 0, it tells me there is no way to write a section of this line bundle which is invariant under the scaling action on instanton moduli space. Now, the determinant, the one-loop determinant, is a section. So it tells us the one-loop determinant cannot be scale invariant and must flow. So the particular quantity that's going to tell us how things fail to be scale invariant is the coefficient of the equivariant parameter. Okay. So I'll quickly go through the essentially two-line computation, which tells us that this quantity is 11 over 3 NC minus 2 over 3 NF minus 1 over 6 NS. And these numbers come out of the Bernoulli numbers. So here's how it goes. We can discard anything which involves u squared, the equivariant parameter squared. And then it's almost immediate that the Todd class, the equivariant Todd class of the tangent bundle looks like this. 1 plus 2h plus u plus 11 over 6 uh, where h is the hyperplane class in twistor space. So this is a very trivial computation which just comes from the formula for the Todd class. The Todd class is given in terms of Bernoulli numbers. And we already see the 11 over 6 appearing. Now, I want to multiply this by the Chern character of the bundle on twistor space. Now, I start with a holomorphic bundle. So this encodes the twistor uplift of my gauge field. And the fields, well, the positive elicited gluons are they live in the adjoint of that holomorphic bundle. The negative elicited gluons, I have to tensor by the canonical bundle. There's some standard thing due to Penrose about how does a helicity and spin that translates into some line bundles in twistor space. So similarly for fermions, well, they're fundamental and anti-fundamental fermions, and the positive and negative helicity fermions live in these line bundles. K to the 1 over 4, K to the 3 over 4. Again, read off this ancient 1960s results of Penrose, and similarly for the scalars. Now, we compute the Chern character of this. How do I do this? All we really need is that the Chern character of the canonical bundle is e to the minus 4ah minus 2au. That's very simple. And we find the Chern character of this bundle, which encodes the field content, has this expression. This is a one-line computation. Now you multiply this by the Todd class. And what you find, when I integrate over twistor space, you find the instanton number times the equivariant parameter, which tells us that things fail to be scale invariant. It's the measure of the failure of scale invariant, times this famous coefficient. Okay? So this is, of course, matches the answer derived from Feynman diagrams. So I feel like I'd like my Nobel Prize now. But what's nice about this is it's like, A, super easy. It could have been done by Grothendieck in 1962. Yes.
When you say super easy, is there, like, now that you know how to do this, can you go back and try to frame it for, like, your first year grad course without twistor theory? Like, how much machinery did you actually need to build up before you could pull that out?
I think you just need twistor theory and the Riemann-Roch formula. So I think you do need a little twistor theory. But that doesn't involve computing any Feynman diagrams.
But is your intuition for
Background field computation doesn't involve computing any Feynman diagrams either. Yeah.
Okay.
What's the relation to that computation?
I actually don't know.
That's also a two-line computation that does not involve.
Okay, well,
Why did we need an instanton?
oh, because in the self-dual theory, the only thing that flows is the theta angle. So we need an instanton to measure that.
In this computation, is there a technical issue with the non-compactness of PT?
No, I don't think so, because you could say you might be looking at an equivariant integral. But the point is, because the second Chern character of this bundle, I assume it's an instanton, so that's compactly supported 2,2 form. I should say, Roland was also able to derive one combination of the A and C theorems using this method. Okay.
The theorem or the values of A and C?
The values. The values of one.
The values of one linear combination, Roland says. Okay. So now we have this, well, I think this is fun. We have this new way of computing the beta function. What I'd like to do is try to study instanton contributions to amplitudes and see what this says about this enhanced symmetry. So I'm going to find some explicit formula and also some very strange phenomena which I would like people's help with. The strange phenomena are related to UV divergences which come from small instantons and how this changes the orgy flow. So what our strategy is our strategy is the following. So we'll start by taking an SUNC gauge theory, self-dual gauge theory, and I'll put it in an instanton background for some flavor symmetry. And then I want to gauge the flavor symmetry. So this means, all that means in this context is that I'm going to integrate over the SUNF instanton moduli space. The Feynman diagrams for this SUNF sector, they will only appear in the one-loop determinant measure. And what the result will be, after renaming NC to N1 and NF to N2, I'll be studying SUN1 times SUN2 gauge theory, self-dual gauge theory amplitudes, where I'm scattering gluons in one sector, and I have SUN2 instantons. So there's a diagram on the next slide. So let's see. So these amplitudes, so here we're going to do the first step. We're going to study the one-loop scattering in an instanton background. And I'm going to scatter one loop, all plus gluons in an instanton background. So if AF is the gauge field, I let dAFX be its density, the instanton number density. And then I can consider its Fourier transform. which is a function of the gauge field AF, the Faber gauge field, and the momentum. So we have this nice formula. The one loop, all plus amplitude, is simply the Park-Taylor factor times the Fourier transform of the instanton density measured at the total momentum. So I'm not going to give you the proof. The proof of this uses our favorite things about studying how you cancel anomalies in twistor space. So, but here's the diagram. I'm scattering these particles. And in the middle, I have an instanton. And the result is Park-Taylor formula times the Fourier transform of the instanton density. Oops. OK. So this formula, suppose this works for any AF, any on-shell AF. If it wasn't an instanton, if it was just some kind of small perturbation of the trivial gauge field, this would be a formula I think many people already know. The famous Malin formula for the one loop all plus amplitude. But well, it generalizes to the case when it's an instanton. OK. Now, let's think about what this says when momentum is small. At small momentum, pretty much by definition, the Fourier transform of this guy, when momentum goes to 0, is the instanton number, because it's just the integral of the instanton density. Let's go back a slide. So if this, sorry, there should be -2. If this was -2k, you would see it looks a lot like the Cass-Moody correlators at level -2k. And that's what we find. If I take this scattering amplitude, now it no longer has to be single trace, and I take the limit as all momenta go to 0, then it becomes the Cass-Moody at level -2k. Okay, so this suggests, and is indeed true, that that these well-known results of Andy and friends, that Cass-Moody algebras appear in soft theorems, gets modified to include a level. So the famous leading soft gluon theorem, of course, predicts we get a first-order pole once the momentum becomes soft. So what we're finding, when I look at amplitudes in the instanton background, we also get a second-order pole when coming from this diagram, when P1 becomes soft. And the second-order pole is the term appearing in the Cass-Moody algebra at level -2k. Now, it's worth pointing out he might be unhappy with me looking at disconnected diagrams and disconnected amplitudes, because most of the time people say, well, I only care about, say, the single-trace amplitudes. The multi-trace amplitudes are just products of them. When we deal with instantons, that's not true. Because if I have multiple traces, they each will have the same instanton in the middle. And I'll be integrating over instanton moduli space. So the statement that it's a product is only true at the level of the integrand. So it's essential to consider multi-trace amplitudes.
Are you integrating over the position of the instanton?
I will do eventually, yes. I haven't done that yet. Yeah, and that will, of course, set momentum to 0. So basically, what we're saying is, Haymitter and Strominger showed the leading soft gluon theorem gives this level 0 Cass-Moody, and here we find a level -2k. And I've showed this at the level of the integrand, but it's going to survive when I integrate over instanton moduli space. I think I'm going a little too fast, actually. I mean, I predict I'm going to run out of slides. I thought I had too many. So, questions, Eva? Yeah.
First is, I guess the levels that I would have been used to in Andy's theory would either be related to higher divergences, and I guess this is different because it's the current versus the memory.
I think my answer to both questions is I don't know. I certainly would expect a gravity analog of this story, but we haven't explored it. I think it would be very interesting. OK. So if we want to go a little further, we don't want to just say that we have this formula saying the one loop all plus amplitude is expressed in terms of the Fourier transform of the instanton charge density. So to go a bit further, we need a formula for the instanton charge density so I can compute its Fourier transform and get an actual explicit answer. So fortunately, there's this very nice result of Hugh Osborne, who shows that if you give me the ADHM data to give you an instanton, the instanton charge density is given explicitly in terms of the ADHM matrices like this. It's basically log of this is like the instanton size, more or less. Anyways, this explicit formula. Now, if I was to apply this to a charge 1 instanton, in the charge 1 instanton, this x is a 1-by-1 matrix, so it's just a scalar. And then this contraction of I and j, I'm going to call that rho square. That measures how big my instanton is. So in that case, you can just compute the Fourier transform. In the higher charge case, we weren't able to compute it exactly, but we can get some asymptotics. In the charge 1 case, this Fourier transform of the instant density is, well, there's some exponential, of course, which we would expect because x controls the center of mass of the instanton. But the important factor here is this Bessel function. It's a modified Bessel function of the second kind. So it looks, if I expand it, 1 minus a quarter rho squared p squared, and then there's this log term at order rho to the 4th. Okay? So if I have a flavor instanton of charge 1, what we find is, I'm assuming the center of mass of that instanton is at the origin for now. The single trace all plus amplitude looks like this. So the first 2 terms are nice. The first one is just a kind of Cas-Moody. I'm missing a sign here. The second term, well, there's a paper of Walker, Struthi, and Andy where they study central extensions of these algebras, and this term appears in that paper. The third term is annoying because it involves logarithms of the momentum. Oops, this always happens. So the third term means even in the all plus case, we're used to finding that the one loop all plus amplitude is this beautiful rational function. It turns out not to be once you include instantons. This tells us it's no longer, the leading soft gluon satisfies this nice Cas-Moody algebra. The subleading one has nice behavior. The sub-subleading one has this weird log, and there's no longer this lovely chiral algebra. Now, at higher instanton charge, you can also kind of compute the small. You can find a similar expansion like this. Okay. Yeah. That's a great question. Absolutely. I don't know. Yeah, I mean, there's a branch cut here. Normally, branch cuts are related. They appear in unitarity from amplitudes of lower loop number. But yeah, I don't know. One answer to Andy's question, so Andy was saying, well, aren't we going to integrate over the center of mass? And if we weren't integrate over the center of mass, then, of course, p squared would be 0. However, this is only the single trace amplitude. The multi-trace amplitude will be a product of such things. And in each trace, we'll have the momenta in that trace. So we'll still find interesting branch cuts in the multi-trace amplitude. The total momentum will be 0, but the momentum in each trace will not be. Okay, so what about large instanton size? Okay. if you go look on Wikipedia or whatever, you'll see that this Bessel function has exponential decay for a large rho. So this says large instantons are suppressed, and like very fast. If you graph this function, it just drops off right away. And there's similar behavior for instantons of higher charge. So when we do the integral over instanton moduli space, small instantons are going to dominate. Now, because this exponential involves both instanton size and momentum, it's a little problematic with single trace amplitudes. So if I was to set momentum equals 0, then this single trace amplitude would no longer be suppressed with large instanton size. And the single trace amplitude would have an I-order divergence from large instantons. But the multi-trace amplitudes turn out to be exponentially suppressed.
Kevin, I should have asked this question earlier.
Yes.
Instantons are Euclidean?
Yes.
Amplitudes are not Euclidean?
Well, I mean, the amplitudes, I'm analytically continuing the momentum to Euclidean signature,
Okay.
and they're analytic functions.
So can I ask another question? So what happens when you're sitting on the poles in the denominator, like this factorization and so into what?
I mean, these poles here are just the standard collinear singularities at tree level.
But usually when you sit on a pole, the amplitude is factorized. It's more important. Here,
Yeah, you should picture I have a circle inside my instanton. I have two gluons coming in, and the pole is like when those gluons meet at a vertex and then progress to this circle. So they factorize into a usual tree-level thing without an instanton, and so it's just the standard collinear singularity at tree level that appears in the MHV amplitudes. So our goal is to, gauge the flavor symmetry. So we need to integrate over the moduli of instantons. So I'm just going to take this formula and take the instanton measure, the one-loop determinant, and integrate over the moduli of instantons and see what we get. Oh, I think I'm getting dangerously close to the end of my slides. So.
Prepare your questions.
Yes. I thought I would be going much slower. I was like, okay. So the moduli of instantons, let's take the real moduli space. Oh, that should be a 1. And for simplicity, I'm going to study the moduli space of a single instanton. It looks like some piece which has finite volume, some compact manifold here. And the next piece is just the center of mass of the instanton. And then there's the instanton size. So the single trace amplitude looks like this. And I'm going to integrate over the center of mass of the instanton, which will set the momentum to be 0. And I have this Bessel function. And, well, we can, it's rather painful to compute the actual one-loop instanton measure. But it's easy to see how it depends on the instanton size. There's a naive factor of rho to the minus 5d rho. That just comes from dimensional analysis. I have rho and 4 x's. That gives me minus 5. But then this has to be corrected by the one-loop beta function. So it's rho to the b0 minus 5. And this is the formula for this integral. And recall, my Bessel function has an expansion like this in small rho. Now, if you look at this expression, you'll see, generically, unless b0 is large, this will diverge at small rho. So there will be UV divergences coming from small instantons. Okay. This is actually my last slide. Yes. Thank you.
And this, I wouldn't ask this question if it wasn't the right question. So let me. About terms looking universal or something funny at subsubleading, I guess, for this gauge theory case. It sounds a lot like subsubleading soft. And so
Yes.
maybe I'm going to try to lead you into your UV issue, Versailles. Is there a sense in which the instanton size is related to these like soft universal limits or not? Or
Yeah, let's go back a couple of slides. Now I have 4 slides left, which is great.
just need to ask.
So yeah, this is the formula with the background instanton, and indeed, the problem arises here, and it does come with the factor of rho to the 4th.
But I mean, like any connection to soft limits, like subsubleading softer, this is completely unrelated.
No, I think this is the subsubleading soft limit. I mean, I take p to 0.
But
I think
why would the instanton size be related to the currents going soft, for example, like soft theorems?
I mean, the scales in the game are like the size of the momentum I'm scattering, and the instanton size. So everything only depends on the product of those.
And this is like, can I relate it though to only one particle going soft or not? Because I thought this was an expression for the full.
This is an expression for the full thing, but you can take, let's see. Yeah, I think if only one particle goes soft, because the issue is here, right? So I'll get, for example, log of a term which is like log of square brackets ij, and if one of them goes soft, you'll get some kind of logarithm there. Okay.
Question?
Yeah, of course.
Please. Yes, okay, I can send you back more slides.
Mm-hmm.
So you mentioned that when you put in the instanton contribution, you have a second order pole in the soft theorem. Is there a nice intuition for why that just modifies the level by a factor of 2?
Oh yeah, the nice intuition is the following. So an instanton on twistor space is given by a D1, D5 bound state. Now, on the D1 brane, there lives a chiral algebra, and it is the Casimudi at level -2 because the fields on the D1 brane, well, I have the D1, D5 strings, which live in the fundamental of my gauge group, and they're bosonic, and there's 2 of them. Because they're bosonic, the level is negative.
Okay. Thank you.
Question. What's the K upper script in the instanton modulus space?
That's just the instanton charge. Okay. So let me go back to my last slide. Okay. Sorry, the previous one. So let's look at this integral. And let's assume that B0 is 4. Of course, you can cook up theories with that, but 4 is not that special. It's just a kind of convenient to illustrate this phenomenon. Then this integral, because this rho 0 p squared k squared, that goes like, as rho to 0, that just becomes a constant, this piece. So this piece becomes, if B0 is 4, this becomes rho inverse d rho. And as my instanton size gets small, we get a logarithmic divergence. Now, it's easy to see from the previous slide, what does this log divergence look like? This is, again, a single instanton. We get this factor of -2. And, well, the divergence just comes from the small rho expansion of the Bessel function, which is 1. So we get -2 times 1 over 1/2 to n1. Now, here is the very mysterious thing. We have a log divergence which looks like this. It cannot be cancelled by any local counterterm. Why is that? This is an operator. If it was to be cancelled by a local counterterm, this expression is of dimension 0. It would be, ignoring the delta function, it's an expression of dimension 0. So it would be inserting into the Lagrangian an operator of dimension 0. And there are no such. it's also quite easy to explicitly write down the non-local quantity, which gives you this. So what we're finding is when I compute the one-loop contributions, the instanton contributions to the one-loop all plus amplitude, they have a UV divergence and a logarithmic UV divergence. Normally, this will provide a flow in the moduli space of coupling constants. And we're finding this divergence changes my theory, but not by changing any coupling constant. What it does is it changes the integration measure on the moduli space of instantons. So instead of looking over the, say, this is the one instanton case, instead of just integrating over the moduli of one instanton, when I flow, I integrate over the moduli of one instanton plus a contribution from the point-like instantons. So I don't know. Does this tell me when B0 is less than or equal to 4? Does the theory exist? I mean, what's going on? I find this very strange. I would appreciate any comments from the experts. OK. And that was my last slide, so I'll stop there. And thank you very much.